Welcome to Optimum Senior High School. I'm a J. Eric and I'll be taking you through some of the courses in elective maths. Today we'll be looking at vectors in a plane. So we'll be looking at the definition of vectors and scalars, and then we'll go through some of the subtopics. Let's begin with the definitions. What are vectors? Vectors are physical quantities that has both magnitude and direction. We can think of vectors as, let's take this as an example. Let's say a plane is in the sky and then you want to find where that plane is. So you want to find the exact location of the plane. You can't just say the plane is 45 kilometers from the earth or from the ground. You have to specify the location of the plane in terms of angle also. So you can see that in vectors you can only specify the magnitude of that quantity, but in addition you must give its direction also. So something like this. Here we are dealing with a two-dimensional Cartesian plane. So let's assume we have our plane here. You can say this is our plane, it's a certain distance from a certain origin, and then certain angle away from, let's say, this is a building. So you see here, we are specifying the location of the plane using both magnitude and direction. And that's what simply a vector is. Now let's come to a scalar. Scalar is just any physical quantity that has only magnitude. Something like your age. If I ask you of your age, you can only say I am 17 years old. You can't say I'm 17 years old, not degrees. Realize that it doesn't make sense. So in terms of scalars, you can only talk about the magnitude of the physical quantity. Okay. Now let's look at how to represent vectors. We can actually represent vectors in so many ways, and then we'll look at some of the ways that you represent vectors. First of all, let's see. These are called block vectors, and then this is called position vector. Here, this vector means that they are starting from A, ending at B. Okay, the arrow head here tells you the direction, and then the length of this line here, it tells you the magnitude of that particular vector. And this is a position vector. Mostly we write it in small letters, and then when you are writing it by hand, you have to underline it to show it's a vector. So these are some of the few ways to represent vectors. We can put vectors in column form or in a row form. So if I'm dealing with two-dimensional Cartesian plane, here the top one is my x, and then the down one is my y, and this is in a column form. And then in a row form, I have the first one to be my x, and the second one to be my y. You can see in a row form, those two figures here have been separated with a comma. But in the column form, we don't use anything like a comma, and then don't put anything here like an overside. This is not a fraction. It's different from a fraction. So what if I'm dealing with three-dimensional Cartesian plane? How do you put it in a row form? That one also is simply, let's use the same figures and then let's add something to it. So in the column form, since here we are dealing with three-dimensional Cartesian plane, you realize I've added the z component, and then in the same way, in a row form, you put the z component, and then you separate each of the components with a comma. Okay. We also want to look at another way of representing vectors. We can also represent vectors in terms of directional vectors. What are directional vectors? They are just vectors that specifies the direction of a physical quantity. So let's say here, coming back to our previous example, but then this time around we're using different figures. So let's say I have my plane here once again. Okay, what are some of the ways that I can specify the location of this plane? I can say I've moved 3 units on the x-axis and then 4 units on the y-axis. We can also represent these vectors. Let's use a block vector here. So let's say we start from A and ends at B. Here this time around, my vectors can be written as 3i plus 4j, all underlined. What's the difference between this and then the other ones? Realize that this time around, I have my plus operator here in between. There's nothing like a comma. Here, we are actually not adding them. It's a way of representing the vectors. The I simply here tells you a vector in the x direction, and then the j here simply tells you a vector in the y direction. The x and y don't have any effect on these figures. The magnitude of these vectors is actually 1. So in another way, they are also called unit vectors. So when you find the magnitude of this vector, they actually disappear and then it has no effect. So this is another way of representing vectors also. So apart from the row and the column, vectors can also be given to you in this form. Now assuming I have my y component, this time around, I can also do it this way. And let's say the y component is 5. You can see the unit vector in the in the z direction is a small k underlined. It's just like I, j, and k. So the I, j, and k here are just unit vectors that point in the direction of the various coordinates. Okay. Okay. Now that we are through with the introduction, I believe we can start some of the works on vectors. Let's look at zero vectors. What are zero vectors? Zero vectors are vectors that has all their components to be 0. So all the components, the x, y, and then the z components, all of them are what? 0. So assuming I have this block vector AB, the component here is 0, 0, or I can also write it this form. Or so you can see all the components are 0, and then just like the name specified, we say they are called 0 vectors. So 0 vectors are vectors with all the components to be 0. Okay, so that's it. Very, very simple. Let's look at inverse or negative vectors. We'll cut it. Okay, so let's use this diagram here to explain what are inverse or negative vectors. Assuming you are walking on this road, you started from A and you are heading towards B. You realize that the direction is in the direction of the positive. What if you are coming back? So here when you are going, you can say I'm starting from A and then I'm ending at B. What if you are starting from A and then you are coming back to B? Realize that it is the opposite of this one. So in inverse or in negative vectors, all what we do is that if I know AB and then I'm looking for BA, BA becomes the negative of AB. That's what simply means by inverse of vector. So if I already know this to be this, to find BA is going to be 6, 5, 6, and then what you have here is called a scalar. It will multiply both the components in it, and then here the final answer is going to be -5, -6. So that's all about inverse vectors. They are so very easy. So this time I want to look at the magnitude of a vector. Let's see a vector. I have a vector CD. What this means simply means that you are starting from C, then you are going to D. And the arrow here gives you the magnitude or the length of this vector. Then the arrow shows you the direction of that particular vector. Here the components are 3 and 4, which means I'm only dealing with 2-dimensional. And then in another way I can also write these vectors as this, where the I and then the J are directional vectors. How do I find the magnitude or the length of this vector? To do this, we put this vector in an absolute symbol here, and then the magnitude of this vector can be found by squaring of the S component and then the Y component. And if you have the Z component also, you also square the Z component. But in this particular example, we don't have the Z component, so we take out the Z component. Okay. Let me quickly draw a diagram to illustrate this for you. How do we do this? From the previous example, if I have this vector, how do I square this vector? So let's say CD. This means that I move the I here tells you a direction in the S coordinate, and then the J here tells you a direction in the Y coordinate. Okay, so how do I plot this particular vector? I move 3 units to the X and then 4 units to the Y. So let's say my 3 is here, and my 4 is here. I have my vector here. I can quickly draw this, and you can see it looks like it's actually a right angle triangle. And then this side becomes my hypotenuse since it's directly opposite to the 90-degree sign here. And right from here, we can use the Pythagoras theory to get the magnitude of this. And then from the Pythagoras theory, the square of this is equal to the sum of the squares of the other two sides. So you can see that's where we get the formula to calculate for the magnitude of a vector. So here, to find the magnitude of the vector CD, this simply becomes square root of 3 square plus 4 square. This gives me 9 plus 16. This is 25. And then 25 is a perfect square. So final answer becomes 5 units. So to get the magnitude of a vector, you just take the square roots of the sum of the squares of the various components. That gives you the magnitude of that particular vector. What if I have one of these components to be negative? Now you should be very careful. Don't say, let me quickly use this as an example. Don't say it's going to be -4 squared, and this is going to be wrong. Realize this will give you 9, this will give you -16, and then you end up getting a complex root or imaginary root, which is very wrong. To actually solve this, what we do is that we put the -4 in a bracket before we square it, and then this ends up giving you a +16, and then you end up with the same result. But then if you forget to put this in a bracket, you end up assuming the negative was on the 3, here you would have gotten you realize that you get a positive answer, but your final answer will be wrong. So always when there's a negative, put that particular component in a bracket before you square it. So with the continuation, let's look at the following subtopics. We'll be dealing with multiplication of a vector by a scalar and then equality of a vector. What do we mean by a scalar? A scalar is just any number. Okay, it could be negative, it could be positive, it could be a fraction. So assuming I have a vector AB, and then I know AB, and then I have CB, and then let's say CB is equal to 3AB. Here, what does it mean? This is my vector AB, and then this vector AB is being multiplied by 3. So 3 here is a scalar and it's multiplying our vector AB. Now what are some of the significance of a scalar? You can tell if two vectors are moving in the same direction or in the opposite, or which one has the highest magnitude by just comparing the scalar. Here, two vectors are moving in the same direction if all of them has a positive scalar. That means they are parallel. So assuming I have a vector, let's say AB, okay, let's say this AB, and let's say this CD. CD here is thrice AB. So you can see that CD and AB, their magnitude is going to change. CD is going to be longer than AB, but then CD and AB are in the same direction because CD is being multiplied by a positive scalar here, which is 3 times AB. So a scalar can also tell you the direction of two vectors. When it's positive, they are in the same direction, so same direction, and then they are parallel. And when K is negative, it means they are in opposite direction, so opposite direction, but they are also parallel. So the scalar here can tell you some properties of the vectors. So here, and multiplication of a vector by a scalar, you just have to multiply the various components. You just have to multiply the scalar by each of the various components. So to find CD here, CD becomes 3 times the component of vector AB, which is 2, 6. And how do you do this? This becomes 2 times 3 or 3 times 2 since multiplication is commutative. And then 6 times 3. And then this gives you 6 and 18. So here the component of CD becomes 6 and 18. Okay. So that's it for multiplication of vectors by a scalar. We can also go to equality of a vectors or equality of a vector. What do you mean when you say equality of vectors? Two vectors are said to be equal if their various components are the same. So if I have a position vector B, remember position vectors are represented by small letters and then they are underlined when writing. In some of the questions, it will be bolded, so you don't have to underline it. But you writing, you can't bolding it, so you have to underline it. So if I have these two vectors, let's say B is equal to vector B is equal to vector A, and all of them are position vectors. And let's say B is equal to 20, negative 7, and then A is equal to let's say negative 7 y, and then here you are asked to find the values of y. Since these two vectors are said to be equal, their components are also said to be equal. So to do this, all what we have to do is just equate them components by component. So here, this is the x component of this vector, this is the y, this is the x, and then this is the y. You can simply say that 20 is equal to y. So therefore, you can say y is equal to 20. So in equality of vectors, we just equate the component parts. So let's look at some of the examples so far in multiplication of a vector by a scalar and equality of a vector. We have some examples on the board. It says that two sides of a triangle are represented by vectors P, which has a component 2, 3, and Q, 3, negative 2. If R is equal to this expression, where R is also equal to 1, negative 5, find the value of the scalars lambda and then mu. So here, realize that we have one vector equated to multiplication of a scalar by the other two vectors. And how do we do this? First of all, let's illustrate this expression with their components. Here, the value of the R here has been given us 1, negative 5, and this is equated to a scalar here, lambda, and then I have my P, sorry, I didn't underline this, and then P here is 2, 3 plus mu, and then we have this to be 3, negative 2. How do we solve this? We have a scalar, and then to solve this, we have to multiply each of the scalars by the component of the vector, and then here we have negative 1. Now this times this will give us 2 lambda, and then this times this will give us 3 lambda, plus this and this will give us 3 mu, and this will give us negative 2 mu. Okay, from here we can equate them component by component, and then we're going to have 1 is equal to 2 mu plus 3 mu, and then here we're going to have negative 5 is equal to 3 mu plus, negative 2 mu. Realize that these are two equations with two unknowns.